Hello, this is Professor Kuehn. Let's continue our discussion of Newton's optics. We just finished talking about his 5 axioms. The last axiom states that the sign of incidence is either accurately or very nearly in a given ratio of the sign of refraction. So what I'm going to do now is I'm going to go through Newton's explanation of this final axiom, which came to be known as Snell's law. So what I'm going to do is I'm going to first read what Newton says and then explain how he explains it in figure 12.1. He says, regarding the implications of Axiom 5, he says, whence, if that proportion be known in any one inclination of the incident ray, 'tis known in all the inclinations, and thereby the refraction in all cases of incidence on the same refracting body be determined. In other words, he's saying that if you know the relationship between the sine of the angle of incidence and the sine of the angle of refraction for one particular angle of incidence for a given set of materials, like air and glass, for example, then you know it for all because the ratio is always the same. So he says, thus, if the refraction be made out of air into water, the sine of incidence of the red light is to the sine of its refraction as 4 to 3. If out of air into glass, the signs are as 17 to 11. In light of other colors, the signs have other proportions, but the difference is so little that it needs seldom be considered. So if you didn't grasp all that right away, don't sweat it. I'm going to explain it in a moment. And then he refers to figure 12.1, and this is the way he explains it. He says, suppose therefore that RS, this is on the next page, I'm going to read it first and come back to the diagram. Suppose therefore that RS in figure 12.1 represents the surface of stagnating water, and that C is the point of incidence in which any ray coming in the air from A in the line AC is reflected or refracted. And I would know whither this ray shall go after reflection or refraction. And then he says, I erect upon the surface of the water from the point of incidence the perpendicular CP and produce it downwards to Q. And conclude by the first axiom. And so let me pause there and let me just show you this diagram. And I'm going to draw it a little bit bigger and step through this diagram so you understand what he's talking about, because it's actually not that hard to understand what he's talking about. So let's suppose we have this surface of stagnating water right here. I'll draw it a little bit bigger. And suppose we have red light, I'm going to go ahead and draw it red, coming in like this and incident at a position C, right there. Okay? So he says what we're going to do is we're going to erect, and we're interested in where this ray goes after it is incident on this stagnating water. So how do we figure this out using this law of refraction that he just mentioned? Well, he says, first of all, we want to erect this perpendicular, and he calls this line PQ. I think it's PQ right here. Yeah, PQ, like that. And we're interested in what happens to that ray of light once it is incident. And he says we conclude by the first axiom, so he's going to invoke the first axiom in order to explain something first. He said we can conclude by the first axiom that the ray after reflection and refraction shall be found somewhere in the plane of the angle of incidence ACP. So if I label this A right here, ACP, that forms a plane, and you might say it's the plane of your computer screen right now, or the plane of the paper on which I'm drawing this. And he says we know by the first axiom that whether this ray is reflected off the surface or it's refracted into the water, it's going to lie in this very same plane, right? Okay, so here's the air and here's the water. So if we continue this downward into the water or upward off of the water, it's going to lie in the same plane. Okay? Now, he says, I let fall therefore upon the perpendicular CP the sine of incidence AD. So let's go ahead and draw a line AD. Okay, and he calls this the sine of the incidence angle. So just remember that the incidence angle is this angle right in here. That's theta incidence, although he doesn't draw it because he doesn't use angle symbols like we do with the theta. He calls that the sine of the incident. The length AD is the sine of the incidence angle. Why would he say that? Well, remember that the sine of an angle is the opposite over the hypotenuse. So sine of this angle theta is going to be the length of the line segment AD divided by the line segment AC. So sine of theta incident is going to be opposite, which is the line segment AD over the line segment AC, right? And so why does he just call AD the sine of the incident angle? Well, you can do that as long as AC is taken to be of length 1. So what he's essentially doing here is he's imagining drawing a unit circle. So I'm going to go ahead and try to draw a circle. See if I do this with any success here. This is not going to look very good, but that's supposed to be a circle of radius 1. And so if AC has a length of 1, then we know that the sine of the incidence angle, sine of theta I, is equal to the line segment AD. And that's exactly what he's saying here. So we let fall, therefore, upon the perpendicular CP, the sine of incidence AD. And now he says, if the reflected ray be desired, I produce AD over to B so that DB is equal to AD. So he's going to continue this line that he started right here, AD, and he's going to continue it over to a point B right here, so that this line segment, AD, has the same length as the line segment, DB, has the same length as the line segment DB. And so now you can see what he's probably going to do with this. He's going to say that this ray, when it reflects, goes through that point right there, the point B. Why is that? Well, that would imply that the angle of incidence is equal to the angle of reflection. And specifically, the sine of the angle of incidence, which is AD, is equal to the sine of the angle of reflection, which is DB. He says, for this line CB shall be the reflected ray, the angle of reflection BCP, that is this angle right here, which I'm calling theta reflected, the angle of reflection BCP and its sine BD being equal to the angle and sine of incidence, as they ought to be by the second axiom. Okay, so that's basically saying that the second axiom is true. The angle of incidence equals the angle of reflection. Now he goes on to say, but if the refracted ray is desired, so we want to know which direction the refraction happens, that is the ray that's going down into the water. If the refracted ray be desired, I produce AD to H. I produce AD to H so that DH may be to AD as the sine of the refraction to the sine of incidence. Okay, so instead of producing this line all the way over D to B, I only produce a D to a point H right here. So DH. And he's saying you can make that of a certain length so that the sine of the angle theta let me go back. So that AD is to DH as the sine of the angles of incidence to the sine of the angles of reflection. Of refraction. So what I do is I produce that line AD over to DH, and DH is smaller than AD. He said DH may be to AD as the sine of refraction to the sine of incidence. That is, if the light is red, as 3 to 4. And about that center, C, and in the plane ACB with radius CA, describing a circle ABE, I draw a parallel to the perpendicular CPQ, the line HE cutting the circumference at E. So what we're going to do is we're going to take this line and we're going to drop it down like this to point E, so that this line FE has the same length as DH. Then if we draw the beam like this, then that is going to be the refracted ray. He says a line HE cutting the circumference E and joining CE. This line CE shall be the line of the refracted ray. For if EF be let fall perpendicularly on the line PQ, this line EF shall be the sine of refraction of the ray CE. So he says if you take this angle here now, that will be the angle of refraction. That gives you the correct ratio of the sine of refractive angle to the sine of the incidence angle. So he says if you've got air to water, as we've got right here, we know that the sine of theta incident has to be to the sine of theta refracted in the ratio of 4:3, which is precisely the ratio that we've constructed here, where this has a ratio compared to this. So AD to DH is in the ratio of 4:3, which is the appropriate ratio for water.